All right, so we're starting the next unit. This is chapter 5, and chapter 5 is going to be our transition from derivatives into the second major part, major category of calculus, and that's going to be integration. Chapter 5 is kind of our transitional period and kind of lays the groundwork for where integration came from, how it was needed to be used, and how it developed with the limit process into the calculus concept that we actually use and have used for years. The big thing we're going to look at is we're going to look at finding areas under curves, because that's actually what we're going to find. That's the second big problem. The first big problem was how to find the slope of a tangent line. We found that with the derivative. And then the second one is how to find the area under a curve. And that's where the integration comes in. And we're going to develop the background of how that actually came to be. First thing, let's consider an object moving at a constant rate of 3 feet per second. If it's moving at a rate of 3 feet per second, then we know that it's not changing speed or anything like that. We know that rate times time equals distance. If you don't know that, well, now you do. The speed times time equals how much distance is going to be covered over that amount of time. So in this case, we could express this as 3t equals d. 3 times however much time passes by is equal to the distance traveled. Now, if we draw a graph of the velocity, then the distance that the object traveled is equal to the area under the line. So what we have here, we have a constant rate or constant velocity of 3 that's signified by our blue line up here, and we have our time measured on the bottom, velocity measured on the side over here. It just happens to be a constant though. And then when we find the area under the curve here, we end up getting 12 feet. Well, not only that, but we can find that if we have a constant rate of 3 feet per second, and over 4 seconds, we're going to move 12 feet. So the area enclosed in this rectangle and the distance traveled equal the same thing. Now, if the velocity is not a constant, not constant value, we might guess the distance traveled is still equal to the area under the curve, and we would find that that is true. So go ahead and file that away. If we have the velocity function and we find the area under the curve, then that area is the distance traveled or the displacement. We'll talk about both of those in a later section. Now, if we're looking at this problem right here, this is an example where the velocity function is 1/8 t squared plus 1. And we wanted to find the area under the curve. Well, we don't really know how to do that quite yet, but let's say we wanted to approximate it. Well, we could use rectangles to approximate the area under this curve. If we used rectangles touching at the left corners, touching the function here at its left corner, that's called an LRAM, a left-hand rectangular approximation method. So all we're doing here, and we're going to do this with 4 subintervals. We're going to break this interval from 0 to 4 up into 4 equal parts that are 1 second each, or 1 as our width. And we're going to use the left-hand side of each one of these subintervals to plug into our function here. So, for instance, we're going to plug in 0. And if we have 1/8 times 0 squared, which is 0, plus 1 gives us 1. So what that means is our rectangle here has a height of 1, and it has a width of 1. That gives us an area of 1. That's where this number comes in, is that it's the area. So when we plug in 1, next we're going to have 1/8 times 1 squared, which is 1/8. 1/8 plus 1 gives me 1 1/8. Now that is the height of the rectangle evaluated at 1. And then all we're doing is multiplying by how wide the thing is to find the area. So we have 1 1/8 times 1 gives me 1 1/8. That's the area of that rectangle. If we use the value at 2 and plug 2 in here, we're going to get 4 times 1/8 gives us 4/8 or 1/2 plus 1, which gives us 1 1/2. That's the height, once again, of the left side of this rectangle. And all we're doing with the left-hand rectangular approximation method, we're taking the left side of the interval and we're evaluating the function at that value. That means we're going to find the left-hand height of this thing. All right, so for the last one, the 3 to 4 interval, we're going to plug in 3 here. That's 9. 9 times 1/8 gives us 9/8 or 1 1/8. 1 1/8 plus 1 gives us 2 1/8. So that's the height here at 3. And then we make our rectangle over the width of 1 unit, and we end up with 2 1/8 for the area of this rectangle. So now if we approximated this thing using our LRAM, we're just going to add these areas up. So the approximate area is 1 plus 1 1/8 plus 1 1/2 plus 2 1/8, which gives us 5 3/4 or 5.75. That's our LRAM, or our left-hand rectangular approximation of the area under this curve. Now looking at this, what do we notice? Is this going to be an over approximation or an under approximation of this function? Well, if we see, we're leaving out area here, 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 and here that's not being counted. So what do we know? This is going to be under approximation. Now, guys, I don't want you to make the misunderstanding of saying that a left hand is always going to be an under approximation. It's not. You have to actually look at the function itself and the application, because sometimes a left hand will be an under approximation, sometimes it will be an over approximation. So be careful and don't assume that a left hand will always be an under approximation. If we had something that, let me change colors here, let's say it looked like this. What do we know about a left-hand approximation method? Well, we chose left here, it's going to be greater than. If we chose left here, it's going to be greater than. So we're going to be an over approximation with the left-hand side there, whereas it was under approximation here. So you just have to look at the function and see how it's behaving to determine whether or not it's an over approximation or an under approximation. All right, now we could also use what's called a right-hand rectangular approximation method. I know this is going to be difficult, but instead of using the left-hand side, we're going to use the right-hand side. So for the interval from 0 to 1, we're going to use 1 as the height instead of 0 to find the height. So we would plug in 1 and we get 1 1/8. And the 1 1/8 here would be the height times the 1 would be our area of 1 1/8. And same thing with 1 to 2, we would use 2. From 2 to 3, we would use 3 to find the height. And from 3 to 4, we would use 4. And then when we plug that 4 in, we're going to get 4 squared, which is 16. 16 divided by 8 gives us 3. Sorry, 16 divided by 8 gives us 2. And then 2 plus 1 gives us 3. All right, so we just used the 1, the 2, and the 3, and the 4 to find our heights for the rectangles here. So if we added these areas, once again, the height is the area because of the width being 1. So the approximate area here ends up being 7.75. Now, once again, look at this one. Is this an over approximation or an under approximation? Well, it's an over approximation because we've got area here and here and here and here that's above the curve. So we're adding more area with our rectangles than we actually have under our curve there. So this is going to be an over approximation. All right, now the last rectangular approximation method we're going to look at here is going to be the midpoint rectangular approximation method. So what that means is exactly what you would think. For the interval from 0 to 1, we're going to use the midpoint there, which would be at 1/2. That's going to be where we find our height of our rectangle. So in this case, halfway between 0 and 1 is 0.5. Halfway between 1 and 2 is 1.5. Halfway between 2 and 3, 2.5, etc., etc., etc. So when we find these numbers, plugging them in here and adding and everything, at 0.5 we get a height of 1.03125. Okay, so that's the height right here. That's this value right there. That's that length. And then times the 1, and that means we have an area for that rectangle of 1.03125. And we just do that for each one of our subintervals here. 1.5, we're going to get 1.28125. And for 2.5, we're going to get 1.78125. And then for 3.5, we're going to get 2.53125. So those are the heights at the midpoint. So here, 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 and here. So the height, or the value of the function at 0.5, the value of the function at 1.5, value of the function at 2.5, and the value of the function at 3.5. That's where these numbers come from, times the width, which is 1, and that's where those areas come from. So when we add these all up, the approximate area is going to be 6.625. Now looking at this one, what would you think this would be? An over approximation or an under approximation? Well, it's not as easy to see here as it is up this direction. But if we look at this part right here versus this part right here, which one has the larger area? The area that's shaded above this or the area that's not shaded here? Well, the thing is, because of this thing increasing, this value right here is greater than this value over here. So we're going to have more that's not included than we are that is extra. So that means this is still going to be an under approximation, but it's not near as much of an under approximation as the LRAM was. Now in this example, we had 4 subintervals. As the number of subintervals increases, so does the accuracy. So while 6.625 is actually not that bad an approximation, I'll tell you what the exact value is in just a second. While this is not that bad on an approximation, if we increase the number of subintervals we use, or the number of rectangles, then our accuracy is going to be that much more. So instead of using 4, let's say we use, well, 8. So with 8 subintervals, we would actually have to split 0 to 4 up into 8 equal parts. So we need to find out how wide our subinterval is first. And that's going to be from 0 to 4 divided by how many subintervals you want to have. So that's going to be 0.5 is the width of the subinterval. So our first subinterval will actually be from 0 to 0.5, 0.5 to 1, 1 to 1.5, 1.5 to 2, 2 to 2.5, 2.5 to 3, 3 to 3.5, and 3.5 to 4. Now, if we're using the midpoint again, that means we're going to go halfway in between here. So we got 0.25 as our first value, 0.75 is our second value, 1.25 is our third value, and so on and so forth. We're just going halfway in between each one of our subintervals here. So 0.25, if I plug that in there, you're going to get 1.00781. That is the height of the rectangle for the first one there. And that's all we're doing. Just stick with the height for right now. If you're catching the fact that that is not the area, that's great. We're going to talk about why in just a second, and I'll point it out. So all we're doing is we're finding the heights. We're finding the v values here. So 0.75 would be 1.07031, 1.25, 1.19531. And all we're doing is we're evaluating the height at the midpoint of each one of our subintervals here and finding the answer. All right, and 3.75 is our last one. So notice we have 1, 2, 3, 4, 5, 6, 7, 8 values, and these values add to 13.31248. Now, if you didn't catch earlier what I was kind of hinting at, you're looking at this and saying, well, wait a minute, we just found that thing just a second ago, and an approximation that was pretty close was 6.625. Now you're saying with more subintervals we're going to have a greater accuracy, but this is 13.31248. That's way off from what was close before. Well, here's the thing. This is not the area of this first rectangle. Why? Well, it's because that's just the height. Remember here, what is the width? Well, the width is 0.5. And the width here, 0.5. The width here, 0.5. The width here, 0.5. All the way across, the width of every one of these rectangles is 0.5. So we have a common 0.5 that we can multiply times each one of these to find the area of each individual rectangle, or we can just add up all of our heights and multiply the sum of the heights times 0.5, and that's what we're going to do. So if we now take the 13.31248 and multiply it by the width of the subinterval, then we get our approximation, 6.65624. Now, I'm going to go ahead and tell you the actual answer for this is 6 2/3, or 6.6 repeating. So right there you can see we're pretty close to it. We're like 1/100th off. So with 8 subintervals, we were able to get pretty accurate to what the actual area under this curve is. Now, there are those 3 methods we just talked about, LRAM, RRAM, and MRAM. But also there are other ways you can do this. You can set your rectangles up any way you want to. There are instances where you can use only inscribed angles and inscribed rectangles, and those are all below the curve, like this. The reason you might use this is if you wanted to definitely guarantee an underestimate of the actual value. Notice here, we're using left hand here, left or right here, it doesn't matter, it's about the same, but right hand over here, the approximation method. And that's all just to keep the rectangles below the actual value of the curve. The reason you would do this, like I said, is to underestimate. Our average is going to be well below whatever the actual value is. Let's say you were estimating the profits on something. Well, if you estimated the profits to be the shaded amount, but it actually ended up being the actual area under the curve, well, then you did better than you actually told everybody you were going to do. So you look better. Okay, another way is to use circumscribed rectangles. They are all going to be above the curve. So where we have the same curve here, instead of using a left hand, we would use a right hand here to get above the actual curve. So we're above there using a right hand, above there using a right hand. Here we use a midpoint to keep everything above it. And then here we use the left hand to keep everything above it. What is this going to do? Well, that's going to over approximate our actual value. So if you wanted to say estimate the cost of something, you would not want to run out of money and be short just in case it wasn't exact. So you would overestimate a little bit, and that way when you came in under budget, once again, you look better. So there are reasons for you to specifically and intentionally overestimate or underestimate things. All right, a particle moves with velocity v equals t squared for t greater than or equal to 0. What is the position of the particle at t equals 3? Find both the left and right approximations using 6 subintervals. So we're looking at this curve right here, and we need to find out what our subintervals are going to be. We're using 6 of them, and the way you calculate your subinterval, that's the first thing you need to do. The way you do it is you're going to have the end of the interval minus the start of the interval. This is going to give you the length of the interval itself. Now the reason it's a subtraction is you may not always start at 0. You may go from 3 to 1 or something like that. So you always want to do end minus start and then divide by the number of subintervals you're going to use. In this case, it's going to be 6. So we have 3 minus 0 divided by 6 gives us 3 over 6 or 1/2, 0.5. Now what this is the amount of your x value should change with each step as you go through the interval. So we're going from 0 to 3, and I want to count off and do 1/2 each time. That's where I get these values here. It makes it easier for me to actually sketch my graph. So let's do left hand first. So if we do left hand, we're going to evaluate at 0, at 0.5, at 1, at 1.5, at 2, and at 2.5. Left hand, remember, we're not going to use the last value. Now I'm going to go ahead and plug this thing in and find all these values for this because I'm going to use that last value on the right hand, but I'm not going to use it on this one. So let's go ahead and find all these values. All we're doing is we're taking these values and plugging them in and squaring them. So we end up with 0, 0.251, 2.254, 6.25, and 9. So left hand, my first subinterval is going from 0 to 0.5. I'm going to use the value at 0. My next subinterval is going from 0.5 to 1. I'm going to use the value at 0.5. Next subinterval, I'm going from 1 to 1.5. I'm going to use the value at 1, etc., etc., etc. So when I put all this together and draw my rectangles, I know for the first rectangle, I'm not going to have any height at all. I'm going to have 0. And then for the second one, I'm going to have a height of 0.25 or 1/4. And then for my next one, I'm going to have evaluated at 1. I'm going to have a height of 1. And then a height of 2.25. And a height of 4. And a height of 6.25. And then I don't use the value at 3, remember, to evaluate it. With left hand, I'm only using the values on the left of the subinterval. And I've got a width of my subinterval of 0.5. So 0.5 times the sum of all these is going to give me a value of 6.875. So that is my LRAM. All right, now I've got all these values right here already calculated for you. I want you guys to try 6 subintervals again, but I want you to do the right approximation. So the RRAM. I did the LRAM, you do the RRAM and see what you can get. Go ahead and pause the video now, give it a try, and then I'm going to give you and show you the solution to this. All right, so here's the graph of this thing. There's the right hand, so notice that you're going to be over approximating this thing. That last one we had was an under approximation. So when we go, we're going to use the 9, but we're not going to use the 0. So we've got 0.5 times 0.25 plus 1 plus 2.25 plus 4 plus 6.25 plus 9. And when we add all those up and multiply by 0.5, we're going to get 11.375. So that's what you should get for your right-hand approximation, your RRAM for this example. All right, so let's answer some questions here. I want you to pause them after I read through them. I want you to pause, see what you can come up with for your answer, and then start the video back and I'll explain to you what the answer is and why. So if f is positive, continuous, and increasing on the closed interval from a to b, then an LRAM is going to give an area estimate that is less than the true area under the curve. True or false, and justify your answer. Be able to explain why you know that. So pause it, come up with an answer on your own, and then come back and I'll explain it. All right, so if we're looking at LRAM, we know for any given curve we're going to have, if this thing is positive, it's above the x-axis. Continuous means there's no skips or jumps or gaps or anything. And if it's increasing, that means it's going up. Now, it could be a curve like this, but it could also just as easily just be a line. We could have just as easily done this line right here. We're going to get the same thing. So if we do LRAM, that means we're going to use, for any subinterval we have, let's go ahead and just use the 2 here we got knocked off. So that means if I go all the way over to here, I'm going to use this value over here as my height. So I have 0 area right there. And here, I'm going to go straight up and plot that point, and that's going to be the height of that second rectangle. So now, it's pretty obvious we missed area here, we're missing area here, so this is going to be an under approximation. Now, the same thing would have been true of the curve itself. If we take all this out, the curve itself would have had a height right there, if I could draw a straight line. So once again, we're still missing all this area and all this area, so it's going to be an under approximation. So that is definitely going to be true. And notice here, it doesn't matter how many rectangles we use. It's an under approximation there. It's still an under approximation and leaving area out. It's still leaving area out. It's not leaving out near as much, but it is leaving area out still, no matter how many numbers of rectangles we use. So it's a true statement. All right, for a given number of rectangles, MRAM will always give more accurate approximation to the true area under the curve than RRAM or LRAM. Now, guys, one of the things I got to warn you about, you got to be real careful. Anytime it says always, that should throw up a huge flag. Because if you can find one example where this is not true, then it's not always. So always is either really easy to figure out that yes, it's true, or it's really easy to figure out no, it's not. And it should be, because that always means it's an absolute. So will MRAM always give a more accurate approximation of the true area? Okay, pause, think about it, see what you can come up with, and then come back and we'll look at the answer. All right, so the answer is false. Okay, you would think that MRAM would always, but the always is the catch thing here. Remember, when we're talking about different functions, there are a lot of different types of functions. And here's the only one I want you to think about. What about a constant function? Well, if we have a constant function, that means we have a function that has a constant value. If this thing has a constant value over the interval from, let's say, 0 to a, what do we know about the MRAM? Well, no matter how many rectangles we have here, MRAM is going to find what? Exactly the same amount here. What about RRAM? Well, it's also going to find exactly the same value, and LRAM, exactly the same value again. So since that's a constant, any number of rectangles we've got is going to get an exact answer, because this is a rectangle in itself. We're just cutting this rectangle up into smaller rectangles, which we can easily do, and we don't lose any value. So this one is false, specifically because of that one right there. There are other instances with different size where MRAM is not necessarily going to give a better approximation, But this one's the one that's a catch-all. It's guaranteed every single time for any number of rectangles that this thing is never going to get, MRAM will never give a more accurate answer. All right, so for this one, if an MRAM sum with 4 rectangles of equal width is used to approximate the area enclosed between the x-axis and the graph of y equals 4x minus x squared, the approximation is what? All right, now I'm going to help you along with this, but I'm not going to actually work it all the way out. You're going to have to work it out. I will show you the answer in a little bit, but I want you to kind of follow along with how to work this out. So we're using MRAM, 4 rectangles of equal width, and we're approximating the area enclosed, this is important, enclosed between the x-axis and this graph. So we don't know where we're starting and where we're ending. We have to figure that out. So what we're going to do is we're going to kind of sketch this graph. Now what we're going to do is we're going to look at this part right here, 4x minus x squared, and I want to find the zeros for this thing. I want to find where it's crossing the x-axis. So 4x minus x squared equals 0, and I can factor out a common x, and that's going to leave me with 4 minus x equaling 0. So my zeros here are x equals 0, so that's where it's going to cross the x-axis right there. And 4 minus x equals 0 is going to give us, when we solve this, x equals 4. So that means that over here at 4, I have the graph, the other place where this graph is going to cross the x-axis. Now, if we go back and look right here and think about what kind of graph that is, because of the negative, and we know it's a parabola because of the x squared, with the negative we know it's going to open down. So it's going to look kind of like this. Wow, that's awful. Let me try that one again. That's bad. But anyway, you get the idea. So you're approximating this area in here. So we're going from 0 to 4 with 4 rectangles. So find your subinterval. 4 minus 0 divided by 4 means that 1 is going to be your subinterval. So you're going to go there to there, there to there. So this is from 0 to 1, 1 to 2, 2 to 3, and those are not equal, but you get the idea. All right, now I've set it up for you. Now you go back and actually calculate the MRAM. Remember the MRAM, if we're going from 0 to 1, we're going to have 0.5. If we go from 1 to 2, we're going to have 1.5. And find those midpoints and evaluate your function at those values to get the height of each rectangle. And then, of course, the width of the rectangle is the subinterval, which is just going to be 1. And add them all together and see what you get. So pause the video, finish working this thing out, and then come back and check your work. All right, the answer is 11, and you should get that. If you don't get that and can't figure out why it's 11, make sure you ask questions. Bring this problem up at the beginning of class next time we're together, and we'll talk about it and finish working it out. All right, next question. If f is a positive continuous function on a closed interval from a to b, which of the following rectangular approximation methods has a limit equal to the actual area under the curve from A to B? And let me change something here. That B should not be the word B, it should be the letter B. As the number of rectangles approaches infinity. So which one of these approximation methods is going to give us a limit equal to the actual area under the curve from A to B as the number of rectangles approaches infinity? Well, here's the thing. We kind of hinted at this, or I did, earlier, because I said that as the number of rectangles increase, this thing gets more, and all of them get more and more and more accurate. So that means if we're going to infinity with the number of rectangles, how accurate actually are we? Well, we're infinitely accurate, which means we're exact on all three. If we're letting the number of rectangles go to infinity, we can use any one of these three and we're going to get the exact answer. So that means that they're all going to be equal to the actual area. So D is the answer there. All three of them. All right, next question. An LRAM sum with 4 equal subdivisions is used to approximate the area under the sine curve from 0 to pi. What is the approximation? All right, so we're approximating the area under the sine curve, so y equals sine x. We need to find the width of the subinterval. Well, remember the subinterval is equal to the interval divided by the number of subs. In this case, pi minus 0 is the length of the subinterval divided by 4, how many we want to break it into. So that's going to be pi over 4. Now that means that's going to be the common width of all of our subintervals. So if we were looking at this, the first thing we would check, once we got to this, we would eliminate any that did not have a pi over 4 as that constant multiple. They all do, so we're not getting rid of anything there. So now, if we were to break up our x-axis from 0 to pi with equal subintervals of pi over 4, we're going to go from 0 to pi over 4. We're going to go from pi over 4 to 2 pi over 4, or pi over 2. From pi over 4, we're going to go up pi over 4 to get 3 pi over 4. And from 3 pi over 4, we're going to add pi over 4 more to get 4 pi over 4, which is pi. So there are our subintervals right there. Now, if we're using LRAM, means we're going to use this one, this one, this one, and this one, but not that one. So we need to find what the sine of 0 is, what the sine of pi over 4 is, what the sine of pi over 2 is, and what the sine of 3 pi over 4 is. And those are going to be the heights of our rectangles as we come across. So those are going to be the values that we actually add. So find all those and figure out which one's going to be the correct answer. Take your time, pause the video, and see if you can figure out which one of these it's going to be, since I worked through most of that for you. All right, the answer turns out to be C, because the sine of 0 is 0. The sine of pi over 4 is the square root of 2 over 2. The sine of pi over 2 is 1. And the sine of 3 pi over 2 is the square root of 2 over 2. Still positive, because remember our sine is our y value, and it's at 3 pi over 4, it's in quadrant 2, but the y values are still positive. So it's going to be C when we put everything together. All right, a truck moves with positive velocity, v of t, from time t equals 3 to t equals 15. The area under the graph of y equals v of t between 3 and 15 gives what? The velocity of the truck at t equals 15, the acceleration of the truck at t equals 15, the position of the truck at t equals 15, the distance traveled by the truck from t equals 3 to t equals 15, or the average position of the truck in the interval from t equals 3 to t equals 15. Well, area under the curve, think back to that original problem we had, and it was going to be the distance traveled. Now, the thing is, we're going to talk, I mentioned it earlier, but I'm going to mention it again. Displacement and distance traveled are not the same thing always. There are instances where they are. This is one of them. And the reason why those two things are exactly the same thing here is the fact that we have positive velocity. We're not changing signs of our velocity. Distance traveled is how far you traveled over the entire time. It doesn't matter what direction you travel. Displacement is just the distance you are from where you started. Like I said, we're going to talk more about that in the future sections of this chapter, but I want you to understand that if this is distance traveled because of the positive velocity, the fact it's always positive. All right, this is one part of a free response question, and it specifically deals with the rectangular approximation method. It says a test plane flies in a straight line with positive velocity v of t in miles per minute at time t minutes, where v is a differentiable function of t. Selected values of v of t for 0 to 40 are shown in the table above. Here are the velocities. Part A. This is the only one that we're doing, because it's the only one that relates to what we're talking about right now. Use a midpoint Riemann sum. Now, a Riemann sum is just the actual proper name for the rectangular approximation method, because that's the guy that came up with them. You'll hear Riemann sum, you'll hear rectangular approximation method, but either way, they're the same thing. But you're going to use a midpoint rectangular approximation method with 4 subintervals of equal length and values from this table to approximate this thing. We'll come back in just a second. Let me finish reading the question. Show the computations that lead to your answer. Using correct units, explain the meaning of that thing in terms of the plane's flight. Well, we haven't got to notation yet for integrals. Some of you guys are recognizing that, though. That is the symbol for taking the integral of v of t with respect to t over the interval from 0 to 40. And what that would find the area under the v of t curve over that interval from 0 to 40. Now, we're going to find the area, but we're going to approximate it using this. So what we're going to do is I'm going to show you exactly the kind of work you would have to show to get full credit on this. You need to tell them what you're doing. So we're integrating 0 to 40 of v of t dt, and we're going to approximate it, and we're going to use everything up here that we need to use. Now, we're doing this in what? 4 subintervals of equal length, which means we're splitting up 0 to 40 into 4 equal parts. Well, that means that we're going to split them up into 10. We're going from there to there, from there to there, from there to there, and from there to there. So 0 to 10 is our first subinterval. 10 to 20 is our second subinterval. 20 to 30 is our third, and 30 to 40 is our fourth. Now, we're using midpoint, which means that we need to find halfway between 0 and 10. Well, that's going to be at 5. Halfway between 10 and 20, that's going to be at 15. Halfway between 20 and 30, going to be at 25. Halfway between 30 and 40, at 35. So these are the values we're actually going to use. So to find our Riemann sum, guys, you can do this in multiple ways. I'm going to do it, I'll show you both ways real quick. The first way is the way that we've talked about, where you do, since it's a common and equal width of the subinterval, where I'm going to write it down first, then I'm just going to add these heights. So 9.2 plus 7 plus 2.4 plus 4.3. Now, we can then add this. This would not be a calculator question, by the way, at least not from this part right here. So when you add all these things up, this is going to give you 22.9, And 22.9 times 10 gives you 229. Now, it says using correct units, explain the meaning. But I'm going to put units here, but I want to find out what they are. Well, where'd the 10 come from? The 10 came from this top up here, which is minutes. And we multiplied that times these values, which are miles per minute. Well, what happens when we multiply minutes times miles per minute? Well, the minutes are going to cancel out, and we're going to be left with miles. Now, that should give you kind of a hint of what this value we just found represents. Well, before I do that, let's look at the other way. You could have literally taken and used individual rectangles. Said, okay, so I've got 9.2 times 10 plus 7 times 10 plus 2.4 times 10 plus 4.3 times 10. And you would still get the exact same 229 miles. But what we did there is we broke it up. There's the height, there's the width. There's the height, there's the width. And we did rectangle after rectangle after rectangle and then added the rectangles together instead of adding all the heights and then multiplying by the width at the end. Either one of these gets the same answer. Now, what does this thing mean? Well, the integral from 0 to 40 of v of t dt represents the distance the plane traveled over t equals 0 to t equals 40 minutes. Okay, that would be enough. You could also have made the statement that the way we did it was an approximation or whatever, but that thing right there, explain the meaning of this so you're not necessarily talking about the approximation. So it represents the distance the plane traveled over t equals 0 to t equals 40. You cannot just say over 40 minutes because it may be 40 minutes going from 40 to 80 minutes. You have to be specific about the 40 minutes you're talking about. Now, also, why can we do distance here? Well, it goes back to that problem we were just looking at a second ago. Because we always have positive velocity, we're not changing direction. If we had had some of these values here that were negative and we did this, it's going to be a little bit different in the way we would have to do it. And we would also have to do displacement here. And we'll talk more about that in the next section, but be aware that because this is all positive velocity and we're not changing directions during this 40 minutes, then it's the total distance traveled. All right, now we will be learning to find the exact area under a curve if we have an equation for the curve. Rectangular approximation methods are still useful, though, for finding the area under a curve if we do not have the equation, such as that last problem where we had the table. There are instances where you're just going to have bits of information or you're going to have data points along the way that you have to approximate things with. This is one of the ways that you would approximate the area under a curve with a bunch of data points. You would use rectangular approximation methods. All right, that's all of this section, and we'll talk soon.